So the next talk is a topic that's near and dear to my heart. It's about submodular function minimization. And I'm sure that many of you know at this point that submodular functions are becoming increasingly important in the area of machine learning. And submodular function minimization is a method that has a very broad number of applications, not just in machine learning, but many sort of technical areas in the world. And it's actually an interesting problem because it wasn't even known to be polynomial time until the very, very late 90s. And this paper is actually, I think this is a very good paper because there was a numerical algorithm that in practice was one of the fastest algorithms for general purpose submodular function minimization that many people, many smart people for many years, many decades have been trying to sort of come up with some sort of complexity analysis for. And I believe that this paper here at NIPS is the first paper to do something like that. So the paper is by Deeparnab, Chakrabarty, Pratik Jain, and Pravesh Kothari. And I'm actually quite happy that this paper is here at NIPS, so I'm going to then give it up to you. So.
Thanks, Jeff, for that rather kind introduction. So as Jeff mentioned, today I'm going to talk about a particular algorithm for submodular function minimization. This algorithm is empirically has the best performance, but our theoretical understanding has been lacking. So my co-authors and I shed some light on this, and the next 20 minutes or so I would like to share this with you. So to begin with, what are submodular functions? So submodular functions are set functions which prescribe a value to every subset of an n-element universe. So in this talk, I'm going to assume that these values are integers. So what makes a function submodular is this diminishing returns property, which says this, that the marginal increase in the function value on adding an element j to a set S is smaller than the marginal increase in the function value on adding the same j to a subset T of S. So if you think of f as a utility function, it basically encodes the dictum that the marginal utility of an element decreases with your endowment. So the more you have, the less you like an element outside. At this point, I would like to caution the audience that the function may or may not be monotone, by which I mean that the marginal increase on adding an element might actually be negative. So for instance, if you've already eaten 5 mangoes, then eating the 6th mango actually may give you negative utility in the sense that it might make you sick. So that's a word of caution. So let's take an example of submodular functions. Suppose my universe is a set of locations where I can put sensors, and given a subset A of locations, I look at my function is defined as the area covered if I put sensors on those locations. So that is a submodular function. To see this, note that if I have an extra sensor j over and above these sensors 1, 2, 3, the marginal increase is the yellow region. But if I have just the sensors 1 and 2, the marginal increase is this green region, which might look yellow in this, but it's larger. And in that sense, it's submodular. It's proof by pictures. Again, this is a monotone submodular function. More sensors you have, the more area you cover. But if you think of a function which is the area covered minus installation costs of the sensors, that might become a non-monotone submodular function. Okay, so why care about submodularity? So I claim that submodularity is all pervasive. And in the last decade or so, there's been a lot of applications in machine learning. For instance, if you want to cluster a bunch of random variables into parts that look as independent from each other, then you want to find a partition that minimizes mutual information, which is a submodular function. There are other examples in image segmentation, structured learning, speech recognition, and so on. And not only machine learning, as in submodularity arises in various other fields like economics, biology, information theory, and so on. So in sum, submodular functions are fundamental objects in discrete optimization. They're like the discrete counterparts of convex functions in continuous optimization. And it's important to understand general purpose submodular function optimization algorithms. So in this talk, I'm going to look at a very simple version, the unconstrained submodular function minimization. So given a function f, I want to find the set S which minimizes f of s. Again, f is not necessarily monotone, so the empty set is not the answer. So how is f given to us? So I'm going to assume that there is an oracle which if I query a set S gives me the answer f of s. So in particular, there are 2 to the n possible queries I can make given the number of sets. So a priori, this might take exponential in n time. And I think what makes submodular functions awesome is that actually this function, this problem can be solved in polynomial time. So this was known since the 80s. The first proof of this was established via the ellipsoid method, but it took around 2 decades to come up with a true combinatorial polynomial time algorithm. And the current best running time is due to Jim Orlin, and it's n to the 6, if you assume that the evaluation oracle is sort of unit time. So today I'm not going to talk about any of these algorithms. Rather, I'm going to talk about a heuristic that predates the polynomial time algorithms. So in the mid-70s, Philip-Wolfe gave an algorithm for a purely geometric problem. So given a polytope, I want to find the nearest point to the polytope from the origin. So minimum norm, Euclidean norm point on that polytope. It's a purely geometric problem. And in 1984, Satoru Fujishige noted that this geometric problem can be used to find the minimum value of a submodular function. So together, this is known as the Fujishige-Wolfe heuristic, or the Fujishige-Wolfe min-norm point heuristic for submodular function minimization. So why should we care about this heuristic when there are already provable polynomial time algorithms known? Well, it works well in practice, and it is illustrated in this graph. It's a log-log plot of the submodular function or cut functions of certain huge graphs. And as you can see, the top cluster of lines are the provable algorithms for submodular function minimization, and the line that is outlier, the better one, is the Fujishige-Wolfe algorithm. So practically, it seems to work well, but what can be proven? So till now, I think the best known running time analysis was this. It's 2 raised to order n square, which might seem ridiculous because there are only 2 to the n sets. But in particular, the algorithm was not known to be better faster than this. So in this work, we sort of improved the situation a bit, and we showed that the heuristic is in fact what I call pseudo-polynomial time. So it runs in time n to the 7 f square, where capital F is the maximum value of any singleton. So ideally, we would like that f to go away, and we would like that 7 to go as small as possible, but that is the current state of things. So in fact, our result is proven, we prove a more general result. So we actually give a convergence analysis for Wolfe's algorithm for a general polytope. And then we use a robust version of Fujishige's theorem, and then we combine them together to get this result in this yellow box. So in the next few minutes, I'm going to talk about these 2 things. Okay. So first, I'm going to say about this reduction of Fujishige, which converts this discrete problem of finding the minimum submodular function to a continuous optimization problem. It's trying to find a minimum point in a certain polytope. So what is the polytope? So given any submodular function, there is this thing called the base polytope. If you've never heard of it, you don't have to look at the math. It's basically a polytope living in n dimensions, and which has exponentially many facets. It has a constraint for every subset of the universe. What makes this sort of fantastic is that even though it has exponentially many constraints, I can optimize a linear function in almost linear time. So there's a greedy algorithm which can minimize or maximize a linear function in n log n time almost. And this is due to Edmonds. And this is, in some sense, the cornerstone of why submodular function minimization is polynomial time. So in 1984, what Fujishige proved is that if you look at this polytope, BF, and you look at the point x star, which is closest to the origin, the minimum norm point, so Euclidean norm point, and you read off the negative entry. So you look at the coordinates where x star is negative. That set is a minimizer of the submodular function. So in some sense, if you can solve this continuous optimization problem, you're done. You can find the minimum value of the submodular function. So now we can try to apply continuous optimization tricks to find x star. But however, most algorithms in continuous optimization are sort of convergent in the sense that they come very close to the optimum, but they might never reach it. So can we say something that if we reach very close to x star, we can still get the minimizer of the submodular function? Can we still solve the discrete problem? So that's the sort of what is in this robust version of Fujishige, which can be deduced from his paper, but we give a proof in ours. So it basically says this. So instead of the minimum norm point x star in BF, suppose I reach close to it. Suppose I reach a point x, which is epsilon close in the Euclidean norm. Then from this x, I can read out a set T. So this is no longer like the negative entries, but something not very complicated. I can read out a set T, and the theorem is that the function value at T is at most the optimum value plus an error of 2n epsilon. So I get an approximate minimizer. And if your function f is integral, and I choose epsilon to be something less like 1 by 4n, so then in fact it will prove that ft is the optimum. So t is a minimizer. So we'll get exact submodular function minimization. So that's all I wanted to say about actually submodular functions. So now I'm going to switch gears, and I'm going to talk about Wolfe's algorithm to find a minimum norm point in a polytope. So it's like a projection algorithm which projects the origin, or you can find any other point onto the polytope. So two things. I would like to clarify that this algorithm is not the Frank-Wolfe algorithm or the conditional gradient algorithm, which is probably more famous, although it's the same Wolfe. And secondly, just as in the Frank-Wolfe algorithm, I would assume that I have an oracle to solve linear optimization over this polytope. Once again, if this polytope is the base polytope, remember linear optimization is an easy primitive. I can do it in almost linear time. Okay, so before I jump into the algorithm, let me just set some simple preliminaries. So given a set of points S, the convex hull is the smallest convex body which contains these points. So in particular, if I have 2 points, it's a line segment joining these points. If I have 3, the convex hull is this triangle, and so on and so forth. The affine hull of a set of points is the smallest dimensional translated subspace which contains these 2 points. So for 2 points, it's the line passing through them, 3 points is the plane passing through them, and so on. So the affine hull always contains the convex hull. So the crucial thing that one needs to, which sort of is the engine of Wolfe's algorithm, is this fact that although finding the minimum norm point in a convex hull is hard, finding it on a minimum norm point on an affine hull is easy. It can be done by matrix inversion. So this is sort of, I think, the crux that runs Wolfe's algorithm. Okay, a definition. So Wolfe calls a set of points as a corral if the following holds. I look at the minimum norm point in the affine hull, and that lies in the convex hull. So note that the minimum norm point can be found in sort of polynomial time. So in some sense, corrals are, by definition, sets where the minimum norm point of the convex hull is easily found. So in this picture, in the picture in the middle, the minimum norm point on that line lies in the line segment. So that's a corral. While the third picture, that's not true, so that's not a corral. The first picture, where S, the set of points S, is just a singleton, I call it as a trivial corral because the convex hull, affine hull, min norm point are just that same point. So that's sort of a trivial corral. So corrals form the basis, and if you want to take one slide away from this talk about Wolfe's algorithm, it's that it's an algorithm which moves from corral to corral till it finds a minimum norm point. So in that sense, it's an active set algorithm which maintains a set of points and optimizes over them. It smells like the simplex algorithm, which moves from one simplex to another for linear programming. One difference is that in the process from going from one corral to another, it has to go through these non-corrals, and in my opinion, that sort of makes this analysis a little hard. Anyway, so let me get into some more details about this algorithm. So it maintains a state. The state is S is a subset of vertices of the polytope, and X is a point in the convex hull. So in the beginning, S is an arbitrary vertex, and X is that vertex itself. It's a trivial corral. Till I get optimal, I run what are called major or minor cycles, which we'll come to in a minute. And these cycles update the state. It updates X and the set S. So I'm at a current state. I have a set S of points, vertices. And if they form a corral, once again, what is a corral? The minimum norm point of the affine hull lies in the convex hull. So if I have a corral, I run a major cycle. So the first thing I do is find the minimum norm point in the affine hull. That's easy to do. That lies in the convex hull just by definition. And now I do the following. So the Wolfe algorithm does the following. It solves a linear optimization problem. So it finds the minimum P, so that Q is the point which minimizes P dot X in the polytope. So in some sense, what it's trying to do is trying to discover another vertex of this polytope which lies in the origin side of the X. So if you look at the hyperplane at X, this Q lies in the origin side. So it's trying to discover a min-norm point, and it adds this to the set S. So that's the end of the major cycle. Major cycles increment the size of S. Okay, so what if S is not a corral? So then this is what it starts a minor cycle. Once again, it finds the minimum norm point of the affine hull. And now, since it's not a corral, this point y lies outside the convex hull, as in this picture. So I have x old, which is the current iterate. I have y, which lies outside. And the new iterate is found by joining the line from y to x old and see where it intersects the boundary of the convex hull. And I move my new current iterate there. So one intuition of why they are doing this, why he is doing this is, y is the minimum norm point, x is the current iterate, and I'm moving towards y, I will actually decrease the norm. So all these steps are decreasing the norms continually. And once I do that, since I'm at the boundary of the convex hull, the current point x can be expressed as a convex combination of these points s, where some of the coefficients become 0. For instance, in that picture, I don't need the rightmost green point to describe this new point x. If I write it as a convex combination, it's just the convex combination of the vertical 2 points. So at this point, it removes these irrelevant points from the set S. So this is what Wolfe's algorithm. This finishes the minor cycle, and the point is that the minor cycle decrements the size of S. Okay, so let me sort of summarize. So I'm maintaining the set of vertices. If they form a corral, I run a major cycle. The major cycle increases the size of S. If S is not a corral, I run a minor cycle, and that decreases the size of S. And it's not too hard to see the norm of the current point x keeps on decreasing, and therefore, in some sense, corrals can never repeat. And therefore, the number of iterations is bounded by the number of corrals, which is, if you look at in a base polytope, it's like 2 to the n square. So it's finite termination, but it's quite large. And that's the only theoretical guarantee that I thought was known for this problem. So what we show is the following. So more precisely, we prove that for any polytope which lies in a ball of radius capital R, n r square by epsilon square iterations of this Wolfe's algorithm will give me a point x, which is epsilon close to the min norm point in the Euclidean norm. So in the case of the base polytope, one can show that this capital R is some polynomial in n, the number of vertices, number of elements, and capital F, and that gives you the pseudo-polynomial time when you set epsilon to be something like 1 by poly n. Okay, so in my remaining time, which is not too much, I would like to give an outline of the proof. Obviously, for more details, please join me at the poster tonight. So this combinatorial way of looking at corrals and how they move around seems a little complicated. So I don't know how to get that exponential bound down to polynomial. So rather what we do is we prove that every time, we basically prove that once we move, as we are moving along in this polytope, we have significant norm decrease if my polytope if my current point is far from the optimum. Now this is a little hard to do. In some sense, the main villain in all this is the minor cycles. When you have more than 2 minor cycles between 2 major cycles, I really don't know how to argue anything like this. But what we could show, it's not too hard, is that if I have 2 major cycles with at most 1 minor cycle in between, I always have a significant norm drop. And then comes a very simple fact that since the number of major cycles increase things by 1 and minor cycles decrease things by 1, and the size of S can be no larger than the dimension, in order n iterations, I will always have such a good pair of major cycles which have at most 1 minor cycle in between. So that's a simple fact. If you have not gotten this, it's not too difficult. So that's all I will say about the proof right now. So to conclude, the Fujishige-Wolfe heuristic is practically the best heuristic known. We did get a pseudo-polynomial guarantee, but it's, I think, far from what is experimentally believed to be the correct answer. In particular, I don't think the little that I have played around with it, there shouldn't be any dependence on the capital F, the value of the function, and also possibly the size of the exponent in n can be decreased. So one thing that so we we got a result about general polytopes, and then we applied it, this robust version, and got this result. I think to get these dependencies out, we might need to exploit submodularity directly when trying to argue about the convergence. So currently, I don't know how, and I hope that, future we can do this. So with that, I'll thank you for your patience and time.
So we have time for one, maybe two questions. And also, may I please ask that the spotlight presenters during the questions quietly come up and line up on this side of the stage in the order that your poster number is numbered. So questions?
Question.
Oh, question. Okay, good.
Yeah, so I was wondering why the standard convergence proof for Frank-Wolfe cannot be applied here?
It can be applied. It will give you a pseudo-polynomial time guarantee, but it seems that the dependence on f does exist empirically.
So what was the improvement from your bound?
So this is an analysis of an algorithm that works in practice, the Fujishige-Wolfe. It's not the Frank-Wolfe algorithm. It does better than Frank-Wolfe in practice, but you cannot use the Frank-Wolfe analysis to get an analysis here.
Okay, so you're saying that you cannot reuse the Frank-Wolfe analysis for
not that I
the
know
min-norm
of.
point.
No,
Okay,
I don't know how to do it.
Okay, so we're actually out of time, but anyways, let's thank the speaker one more time.